All right, I think everybody is almost seated. Almost everybody is seated. I think we can resume. We'll have the second talk today about thermal EFTs for CFTs by Yixin.
Okay. I'd like to thank the organizers for this invitation. And today I want to talk about thermal EFTs for conformal field theories. And this is based on a recent paper with Nathan Benjamin, J.H. Lee, Shredder Powell, and David Smith-Duffin. Both Nathan and J.H. are in the audience. So what is a thermal effective field theory? What I want to convince you is that thermal effective field theories provide a framework to organize the information about the conformal field theory in such a way that it often reminds you of modular invariance in 2D CFTs. Hopefully by the end of my talk, it will be clear why that is the case. Let me start my talk by quickly reviewing what is thermal effective field theory, what they are and what they are good for. So the object of interest is the partition function of my CFT with some angular fugacity turned on. So let me write it as trace evaluated as in the Hilbert space assigned to a sphere e to the minus beta h minus dot some j, where these j's are just Cartan generators in SOD. Closer? Is it better now? Okay. To evaluate this partition function, I want to compute the path integral on S1 beta times SD minus 1 with radius L with some twist by beta omega. What this means concretely is that as I travel as the sphere travel along the thermal circle, I want to apply some small rotation by beta omega and then I glue them. So more concretely, I want to couple my CFT to the following metric. Which is ds squared plus. Here I'm expanding the metric on the sphere using the radial coordinate and angular coordinate. So basically what I'm doing here is I want to decompose my d-dimensional Euclidean space into a set of non-intersecting planes, and all these RAs and theta A's are all the polar coordinates on these non-intersecting planes. And this is just metric on the sphere. Right? Okay, to implement this angular twist, I want to make the following identification of coordinates. As I advance by beta in the tau direction, I'm also shifting on the thetas. Now I can do some, sorry. So what are this?
Could you draw a picture what's going on? What is this?
So what I'm doing is, this is a metric on SD minus 1, which I can embed in RD. And then I can decompose this d-dimensional Euclidean space into a set of non-intersecting planes.
But
and then on each
depends
of
whether D is even or odd.
Yeah, depending on whether D is even or odd, you might have some like remaining direction. So, okay, let me be more precise. Now, this A goes from 1 to, let's say, the floor of D over 2 plus epsilon. And depending on whether D is even and odd, this epsilon can be 1 or 0. That epsilon just takes care of the remaining direction. Okay. No, I'm just...
Can you draw a picture? I don't know. Let's consider some example.
Okay, okay, then if D is 3, what happens is that, let's say I'm choosing my R, the A is just 1. So like R and theta are really just the polar coordinates on this plane. And then I have, this is my R2 direction.
I see.
So the sphere is okay. Sorry, the SD minus 1 is the submanifold given by RA squared, sum up to 1. Does this make sense?
Now it's better, thank you.
Yeah. Or another way of saying this, we all know that, okay, for S3, we can write it as Z1 comma Z2 in C2 such that V1 squared plus V2 squared is 1, right? And how do I expand the Z1 and Z2? Well, Z1 is just R1 e to the I theta 1, and Z2 is just R2 e to the I theta 2. Okay. All right. Let me maybe, can I erase this? Sorry. Okay, so now I can perform some change of coordinate and massage this metric into the Kaluza-Klein form. Now, all these background fields, the D minus 1 dimensional metric, the Dilaton field, and the KK gauge field, they can be expressed as some complicated functions of beta, omega, and also the coordinates on the sphere. The details of these functions are not too important, and I'm not going to write them down for you because they look a bit lengthy. But what I want to say is, once I put my CFT in this geometry, I can start to compactify the CFT along the thermal circle. And then I will arrive at a quantum field theory in D minus 1 dimension. Generically, after this compactification, you would expect the D minus 1 dimensional quantum field theory to be gapped. Well, of course, there can be many counterexamples. For instance, if you start with a D-dimensional free scalar, and then you do this compactification, you will have a zero mode. And also, if you do supersymmetric compactifications, you also have gapless modes after the compactification. After you go to D minus 1 dimension. But we are not going to focus on those cases here. So in what follows, I will always assume that the CFT compactifies to something with a mass gap. So once I have a gapped quantum field theory, I can write down an effective action to capture the large distance physics. What this means more concretely is, okay, before the compactification, I have my partition function for the CFT, which is the same as a partition function of the D minus 1 dimensional quantum field theory, which depends on, of course, all the background fields. And then I should be able to write down an effective action, which I call S thermal. And then the effective action depends only on the background fields. Here I'm writing a wiggly sign. What this wiggly sign means precisely is that both sides of this equation would agree up to exponentially suppressed terms, such as e to the some number L over beta. So this is, terms like this is what we call non-perturbative corrections. Okay. The nice thing about this effective action as thermal is that the terms in as thermal are highly constrained. They should first satisfy d-1 dimensional coordinate invariance. Plus gauge variance. Well, this, of course, just follows from d-dimensional coordinate invariance. But since the quantum field theory comes from the compactification of a CFT, as thermal should also be constrained by d-dimensional Weyl invariance. What this means more concretely is that if I rescale the metric, rescale the d-dimensional metric, the partition function of the CFT should not change unless your CFT suffers from a Weyl anomaly, in which case I need to add some additional anomalous terms in the thermal effective to the action in order to capture the anomalous transformation of the partition function on the rescaling. But Weyl anomaly is not going to be too important for us today. Okay, now I can start to just enumerate terms which satisfy these two requirements. And I can enumerate them and then I can organize them into a derivative expansion. Since I started with a theory which is scale invariant, I know that this derivative expansion would also give me an expansion in 1/beta. Here I wrote down the first few terms in this derivative expansion. What are they? Well, they are the cosmological constant terms, and the Ricci scalar, and also the Maxwell term. Each of these terms comes with an unknown coefficient in front of it, which are just the Wilson coefficients. And generally for a CFT in d greater than 2, we will have an infinite, okay, actually, these are the Wilson coefficients. For CFTs in dimension greater than 2, I will usually have an infinite set of Wilson coefficients. And this Wilson coefficients will contain information which is intrinsic to the CFT. So they are the theory-dependent data here. Now I can express all the Ricci scalar and also the field strengths in terms of beta, omega, and also other coordinates on the sphere, and then I can just perform this integral explicitly. What I will end up with is the expression in the second line. By basically writing the R and F as explicit functions of beta and omega, and also R theta. Well, and then just perform this integral by brute force. Yeah. What is capital F? Oh, F is dA. And then A is the KK gauge field. Oh, I should also mention that here G hat is a rescaled metric in d-1 dimension, rescaled by the Dilleton field. And the only place that the Dilleton field comes into this expression is through this rescaled metric. And this is a consequence of Weyl invariance. Okay, at this point, I want to make a few comments, which is that the thermal effective action is actually very flexible. What does that mean? So suppose I choose some arbitrary d-1 dimensional manifold. Let's call it MD-1, which is different from a sphere. I can assign a Hilbert space to this d-1 dimensional manifold. And then I can try to compute the partition function in this new space. d-1, e to the minus beta h. I probably also can twist this partition function by some group elements in the isometric group of the manifold. I will just denote it by e to the minus beta c dot q. Now what I can do is that in order to compute this new partition function, I can just set up new coordinates on S1 times MD-1. And then I write the metric in the KK form. I compactify my theory down to MD-1. And then I can just write, I should be able to express this partition function again as e to the minus f thermal. Now, this thermal effective action will have exactly the same expression, will have exactly the same term here, and it will have the same set of Wilson coefficients. The only difference is that now the R and the F will have a different expression in terms of beta and also viscosity. And they will also depend on a new set of coordinates, which are coordinates on MD-1 instead of coordinates on a sphere. But you can basically just follow the same procedure and arrive at a different expansion, which computes the new partition function. So in this sense, the thermal effective theory allows you to separate the information which is intrinsic to a CFT that are captured in its Wilson coefficients from the information that is specific to the background you put the CFTs on. Okay. Another thing I want to mention is that, let's say if you start from a CFT that suffers from gravitational anomaly, then you would have to put additional terms in the effective action. These are what we call the topological terms. What did it look like? Well, usually they are the gravitational transimpedance term or transimpedance terms built out of the KK gauge field. These terms are not gauge invariant, but the coefficient in front of them will be fixed by the anomaly, the gravitational anomaly in the d-dimensional theory. We will briefly come back to the topological terms later. Okay, all this looks super complicated, but to orient ourselves, let's look at what happens when d equals 2. If we go back to this expression, we see that when d equals 2, the second term vanishes. And as a matter of fact, all the dot 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 also vanishes. So for 2D CFTs, the only term you can write down in a 1D effective action are the cosmological constant terms. So in this case, S thermal greatly simplifies, which is just 2 pi f. Now this Wilson coefficient f is known to be related to many important quantities in finite temperature CFT. In particular, for a 2D CFT, it evaluates the vacuum energy on the circle. Now this immediately tells me that F is related to the central charge in the following way. Okay, now let's plug this back in and see what we get. Sorry, I should write wiggly sign. Wiggly sign again means agree up to exponentially suppressed terms. Okay, maybe let me just write equal sign plus some non-perturbative corrections, which takes the form some number multiplied by L divided by beta. Okay. But this result should look very familiar to you, because you can reproduce this from the S invariance of the torus partition function. If you go through this calculation carefully, you will see that the thermal effective action captures the contribution from the ground state from the modular dual channel. On the other hand, all these non-perturbative corrections are coming from the excited states in the modular dual channel. Okay, as we all know, in 2D...
Sorry, can I ask a question? So here you're using that your effective action is just fixed to all orders in the derivative expansion in 1D because there's nothing else you can write?
Yes. Right. So from the point of view of thermal effective action, what's really special about 2D CFT is that you only have a single Wilson coefficient as opposed to higher dimensional CFTs where you have an infinite set of them. All right. So as we know that in 2D CFT, modular invariance allows you to write down the asymptotic density of states for very large delta. And this is just the famous Cardi formula. But, okay. Similarly, using thermal effective action on, it's a sum of terms, sorry. I should write ... And then this bracket extends here. Okay, in 2D, we have Cardi formula, and similarly for higher dimensional CFTs, using thermal effective theory, we can also write down the asymptotic density of states as a function of all this Wilson coefficient. I can also write down the asymptotics of heavy OP coefficients, again as a function of the Wilson coefficients. And these are explained in a paper by Nathan, Jeha, Hiroshi, and David. But this will not be the focus of today. This is the archive number of the paper. So, in today's talk, I want to look at a slightly different object, which is a spin-refined partition function with finite angular fugacity. And what is that object? Well, as an example, minus 1 to the power j e to the minus beta h is an example of spin-refined partition function with finite angular fugacity. And I want to compute the high energy asymptotic of the spin-refined partition function to the untwisted ones. What I hope to explain to you is that the asymptotics of the spin-refined partition functions can actually be determined by the same set of Wilson coefficient as the usual untwisted partition function, up to some subleading corrections which show up at certain combinations of angle. Okay. And if time permits, I will also say a few things about the non-perturbative terms. And hopefully, by now, I've convinced you, or I've showed you that thermal effective theory somehow carries a flavor of 2D modular invariance. So in the rest of the talk today, what I want to do is that I want to extend this analogy beyond S transformation. And also I want to extend this analogy beyond the vacuum state in the modular dual channel. Okay. Okay. For a higher dimension, yes. Yes. The last line. Sorry.
So what is the range of omega you are considering here?
The range of omega. Oh, that's a. Sorry.
Yeah, I'm asking because if for 2D CFT, if you have some chiral current, then you can tune omega to be very close to ±1. Then the contribution from chiral current will beat the contribution from vacuum.
So let's see. Here, in order for the thermal effective theory to be valid, I only need, I need beta, I'm actually allowing this omega to be of order 1.
Order 1, but it can't be very close to ±1 or not. I think this is, when it's close to ±1, it's very subtle to write down this, to say vacuum is dominant.
Okay, you're worried about the vacuum dominance in the modular dual channel.
Yeah.
Well, what I can say is that from the point of view of thermal effective action, I am actually allowing this omega to be very close to 1. But there are some there might be some subtleties which are not captured by the thermal effective action.
Okay.
And I think it would be very interesting to understand where that action comes from, where that subtlety comes from.
Thanks.
What is special about omega equal 1?
Sorry.
So in this formula, nothing special happens for omega equal 1, right?
Yeah, nothing special happens for omega equals to 1, but something special would happen if you set omega to ± I, because.
Yeah.
Right. But I think what Jiaxing is thinking is that.
No, because I did some computation for 2D CFT with chiral currents. Then if you tune beta to be very, very small and omega very close to ±1, it can happen that the partition, the contribution from current is much larger than the contribution from vacuum. This is.
I think you mean omega beta time, close to 1, right?
I think I mean omega close to 1. Maybe -1. Are you sure?
Yeah, because.
Okay. Maybe you can discuss later here.
All right. Okay. So let's continue with our discussion of twisted partition functions. Oh, this is very bad. Before I give you all the details, I want to first state our conclusion. So let's choose R to be some element in SOD. And I require R to be an element with finite order. And I will denote the order of the element R by Q. Let's look at some examples. So if R is, let's say, -1 to the power j, then the order is just 2. And let's say if R is, yeah, you can take it. So in higher dimension, you can turn on more Cartan generators. And well, in this case, I'm writing down an element in SO4. And then for this element, Q will be taken to be 15. Okay? Now, if the subgroup generated by this finite order element R acts freely on the sphere, then here is a prediction from thermal effective theory. The asymptotics, the high energy asymptotics of the twisted partition function will be will be equal to, up to non-positivity corrections, 1 over Q times the effective free energy of the untwisted partition function, but this time with a larger inverse temperature. For CFTs with suffering from gravitational anomaly, we also need to be careful about the change in topological terms. I will make a few comments about this line later. Okay. In a case when the subgroup X, the subgroup action is not free, well, for example, if I have something like e to the 2 pi I p j over q as an element of SO3, then this element will rotate you around the z-axis, but on the two sphere, the north pole and the south pole will be fixed under this rotation. So this is an example of a non-free action. In the case when the action is not free, then the prediction from the thermal effective action looks almost identical, except that, let's see if I make it. Good. Except that in this case, I have some subleading corrections, which comes from what we call defect actions. Okay. I'll explain in a minute what this defect action means. All right. So these are our main results. In the rest of my talk, I will try to convince you that this is true, and I will try to explain where this comes from. Okay, but maybe before I start to explain, I should first justify the problem. Because some of you might be thinking, this problem is just completely trivial. Because in the very beginning, okay, where is the equation I wrote down? Yes. Okay, in the very beginning, I've already written down the high temperature asymptotics of a twisted partition function that involves some sort of angular twist. Now, remember, like here for me, R is really e to the I theta dot j, where all the theta i's are some rational multiples of 2 pi. Well, they are of the form like 2 pi pi over qi. So you might be tempted to say, okay, why don't I just set beta omega to be theta? And then I can just plug in the expression of omega as theta over beta, plug it into this formula, and then I declare victory. Why do I have to spend an extra 20 minutes explaining the twisted partition function with finite angular fugacity? Well, as a matter of fact, if you do this naive substitution, it actually creates a problem. So if we look at the expression of the thermal effective action here, we notice that if omega is of order 1 over beta, then the last term I wrote down here would be as important as the first term. Now, due to the size limit of this whiteboard, I can only write down the first few terms, but if you go to higher and higher order, you will see that every beta to the power, let's say, d minus 1 plus k, every factor like this is always multiplied with omega to the power k. Right. So what this means is that terms with very, very high derivative order would be as important as the first term. The whole expansion would be completely reshuffled. And this is a sign which tells you that the original thermal effective theory would break down if I naively substitute beta omega to be theta. So more intuitively, what's happening is that you can basically think of this omega as some sort of angular velocity of a spinning sphere. Now, what happens if you keep beta omega to be a finite number, what happens when beta goes to 0 is that the sphere will start to spin with with an infinite angular velocity. And this would cause the original thermal effective theory to break down. So the punchline is we can't do this substitution. Okay, but now the thermal effective theory breakdown, what should we do? So the idea is to perform some sort of coordinate transform that makes the insertion of -1 to the power j look more like some sort of global symmetry. And we will refer to this coordinate transformation as a folding trick. Okay. To keep things simple and to explain how the folding trick works in the most naive setup, let me just focus on trace -1 to the power j e to the minus h in, well, a 2D CFT. So to evaluate this twisted partition function, I have to evaluate the path integral on a torus. And this is my thermal circle, which is of length beta. And because of this insertion -1 to the power j, as I advance by beta along the thermal circle, I am forced to do a rotation by pi. So this is why I have to identify the edges, well, in a funny way. Let me label this one by this arrow. So what I want to do now is to cut this torus into 2 pieces in the middle and interpret the original CFT as 2 copies of CFT living on a half torus. There is a second piece going behind it. Okay. Sorry, I'm not doing this correctly. Okay, now in the second picture, -1 to the power j no longer acts as a rotation. It acts as some sort of global symmetry that permutes the 2 copies of CFT. Okay. Now what happens is if I start from the first copy of the CFT, I advance by beta along the thermal circle. I would have to go through a -1 to the power j action, which shifts me to the second copy of the CFT. In order to go back to where I start, I would have to go through the thermal circle again. So in this case, the effective inverse temperature will become 2 beta.
It's a bit confusing in this second picture in the middle, you know, what happens with the gluings on vertical lines, because...
Oh, yes,
you know,
let me label the edges here. So I'm basically taking the copy at the back and then put it on top of the first copy on the front.
Okay.
And you can trace through how the edges, the vertical edges, are glued in this picture. Does this make sense?
Well, it's clear, but yeah, it's not clear yet. Why is this helpful?
Yeah, okay, why is this helpful? The nice thing about going to this new geometry is that I can now, I don't have to, in this new geometry, I don't have to perform this large rotation anymore. So I can apply the idea of thermal effective theory again, here in this new geometry, where I have a spatial slice with length L over 2, but a thermal circle with length 2 beta. Okay. So the spin refined partition function will be.
But there is still something very strong going on because you have to glue the horizontal.
Yeah, you're complaining about the side identifications on the vertical lines, right? Because well, like this one should be glued to this one. Is this your complaint? Or
is it not a violent? I mean, so you were worried in the first picture that there was some violent operation going on, which would break down the effective field theory. Now, in the second picture on the right, there's still something violent going on because you have to glue two pieces which seem to be quite far away. So
good. This is
not
good.
obvious why the second violent thing is better than the first.
So the idea is that I want to look at the behavior of the partition function in a beta goes to 0 limit. So in the beta goes to 0 limit, the thermal circle basically gets squashed down. And so that's why the thermal effective action, it doesn't really care about this violent transition on the in the vertical direction. However, as I will explain to you later, the topological terms do care about this violent change. But let me go on. So now I want to write down the thermal effective action in this new geometry. Well, how does things change? Well, so first of all, the effective temperature becomes 2 beta instead of beta. So all the coefficient. Remember that in the expression of the thermal effective action, there was some beta floating around. I should replace all of them by 2 beta. In addition to that, now the thermal effective action is defined on a spatial slice which has length L over 2 instead of L. So that means I need to put an extra 1/2 in front of the thermal effective action. Okay. And let's plug in the numbers.
Can you say again why 1/2?
What?
Can you explain again why 1/2?
Oh, because the original thermal effective action is well, it's computed on a spatial slice, on a spatial circle that has length L. Now I evaluate the same Lagrangian on a halved circle. And that's why you need an extra 1/2. Okay. All right. L over 12 beta. All right. This will be the first prediction coming from the folding trick. But since I'm looking at the 2D CFT, I always have modular invariance. You can ask, can I reproduce this result from modular invariance of the torus partition function? The answer is yes. This result also follows from modular invariance. This time, not modular invariance under S transform, but modular invariance under a different PSL to the element, which is -1, 0, 2, -1. Okay. All right. Now I want to go back to Slava's complaint earlier, which is that if you look at the picture on the right, you will notice that as I travel around the spatial slice, I'm also forced to advance by beta along the thermal circle, right? To say things in a fancier language, this means that the thermal circle now is non-trivially fibered over the base manifold. Why doesn't this cause a problem? Well, the answer is the thermal effective action doesn't really care about the topology of the circle bundle, but the topological terms do. So if you start with a d-dimensional CFT which suffers from gravitational anomaly, and then you go through all the same procedure, and you want to use folding trick, you have to keep you would have to keep track of how the topological terms changes. I will not dive into the details of topological terms in this in this talk, but I just want to give you a quick explanation. Okay, I just want to give you a quick explanation of what this line means. Okay, now let's go back. So actually, the correct way to think about this manifold is that it's S1L times S12 beta. The whole product taking, you want to take the whole a Z2 quotient of this product. So this manifold is not the same as simply taking the quotient of the spatial slice and times a longer thermal circle. These two are not the same, because this one is a trivial bundle, but like the right-hand side, you don't have a trivial bundle. And this would lead to a change in topological terms. And recall that the topological terms show up whenever your CFT has a gravitational anomaly.
Maybe you were already answering this and I just didn't understand what you said. But are you assuming effectively there are no fermions? If there were fermions, then you start there with periodic boundary conditions, but then now you could have anti-periodic boundary conditions on that contribute to the second one.
Exactly. So basically what happens is that if you have fermionic theories, you can, a priori, you can have two different types of boundary conditions along the thermal circle, the periodic one and anti-periodic one. So what happens here is that the folding trick sometimes would mix the two different spin structures. Because, for example, if I start with an anti-periodic boundary condition here, I stack two anti-periodic loops together, I would end up having a periodic spin structure. At the same time, since we know that, for fermions, if I perform a 2 pi rotation, I will pick up a minus sign. So every time I perform a 2 pi rotation, I will have some additional minus signs, and that would also change the effective spin structure as well. But you're right in the sense that folding trick tend to mix different spin structures. All right. And from this picture, it's also clear what happens if I replace -1 to the power j to, let's say, e to the 2 pi I p over q. You just need to divide this torus into q different pieces and then stack them on top, cut them and then stack them on top of each other. What happens is that you basically just replace this 2. I want to say that this will give me all right. So much about 2D CFTs. P dependence? Oh, good. You're asking about whether the spin-refined partition function would depend on P. The short answer is, for bosonic theories, if you only care about thermal effective action, then no, P doesn't enter the game. But if you start to look at fermionic theories, or if you start to look at topological terms and defect actions, the numerator matters. Okay, let's see. All right, the prediction from thermal effective theory can be reproduced by modular invariance in 2D CFTs. But once I go to higher dimension, I don't have modular invariance anymore. However, the folding trick will still go through. the CFTs. So in higher dimension, I don't have modular invariance, but what I can do is that I can basically just replace this spatial circle by, let's say, I can replace it by SD minus 1. I can even replace it by an arbitrary D minus 1 dimensional manifold, and then replace minus 1 to the power j by some other element in an isometry group of MD minus 1. As long as the isometry operator that I insert acts freely on the space manifold, the whole argument would go through. And then the prediction would carry over to higher dimensions. No modular invariance, but folding trick still works. So let me write down the prediction in higher dimension for you. In its most generic form, even if I care about the partition function on a in a slightly different Hilbert space, I can still express it in terms of the thermal effective action. It's just that this time I have to do the integral. Oh, sorry. I can still write. Oh, it's coming back. And this is good. Okay. Now I want to make a few comments about this expression, about this equation. So, notice that if we only care about the leading order contribution to the effective free energy, which is basically minus log of the partition function, then I can just throw away all the Ricci scalar and the Maxwell term. I can throw away all the higher order terms and then only focus on the cosmological constant term. Oh, sorry. Yes. I forgot to mention here that R is of order Q. That's where the Q comes from. Sorry. And also, I made a mistake earlier. Thanks. This should be Q beta instead of beta. Okay. So what I want to say is that if we only care about the leading order contribution to the effective free energy, then we can only keep we can keep only the cosmological constant term and forget about the rest. In fact, as I will explain later, even in the case when the action of R is not free, we will have to add some defect actions. But the contribution from the defect actions is always subleading. And what this means is that it doesn't matter which CFT you're looking at, and it doesn't even matter which Hilbert space you're computing your partition functions in. As long as your CFT compactifies to a quantum field theory which is gapped, you know that your effective free energy would always be scaled by the effective free energy always be rescaled by a factor of q to the power minus d, where d is a dimension of the CFT, after the insertion of the symmetry operator R. And this result, it is completely universal. All that I ask is that your CFT compactifies to something with a mass gap. Okay, actually, how much time do I have left? Okay, then I want to quickly go over the defect action.
Sorry, maybe, is there a way we can test this? Is this like you have some prediction now? Can you look at some explicit theory, ideally 3D, something interacting like 3D easing?
Actually,
that this works?
We checked for a lot of free field theories and also for holographic theories, and this prediction holds.
But can you plug in numerical data from 3D easing, or do you not have enough?
Yes, for 3D easing, I think we try to plug in some numerical data, but I would say that the result is a little bit inconclusive. Yeah. Okay, that's mainly because, well, somehow we have more even spin data than the odd spin data, and then that makes it hard to really verify this conjecture. Okay. Okay, so far I've been focusing on the case when the group R acts freely. But now let's ask what happens when the action of R has a fixed point. Well, when the action of R has a fixed point, and then you look at the quotient of the sphere under the group generated by R, the quotient manifold will start to have singularities. And then to account for this non-smoothness of the geometry, you want to define some defect action which are localized on the singular locus. SD minus 1. It's not smooth. We need defect action. Let's call it SD for D for defect. So these defect actions are localized on the singular locus. And then the first comment I want to make is that the contribution from the defect action is always subleading. And why is that the case? Well, in any kind of derivative expansion, the leading order contribution always comes from the topological constant term. And by dimensional analysis, you know that the cosmological constant term, which is paired with some Wilson coefficient f tilde, and this f tilde is not the same as the f that I wrote down in the bulk action. So by dimensional analysis, I know that the contribution from the cosmological constant term should always be f over beta to the power d, where d is the dimension of the defect. Since we know that the dimension of the defect is always smaller than the dimension of the sphere, so the contribution from defect action is always subleading. Okay, now maybe let's look at a concrete example. Let's look at 3D CFT with the insertion of e to the 2 pi ip over q. Now, this element will rotate you along the z-axis. So the north pole and south pole are fixed under the rotation. So you would have to write down a defect action localized on the north pole and another defect action localized on the south pole. Yes. Am I running out of time?
Remember there was a 1 hour talk?
Oh, okay. So let's see. Let me just write down the defect action to give you like a sense of what it really looks like, and then I will finish there. Sorry. Okay. So the idea is still very simple with the, well, the idea is similar to how you could enumerate terms in the thermal effective action, which is, the only difference is that this time, you only require the terms in the defect action to be invariant under the subgroup generated by R. You don't really require them to be invariant under the whole SOD. So you have more flexibility. You have more flexibility. Okay. Okay, I only write down the first two terms in the defect action. What I want to emphasize is that, okay, all this A0, comma P over Q, they are Wilson coefficient in the defect action. So unlike in the thermal effective action, all the Wilson coefficients themselves, they are sensitive to the rotation angle. And for bosonic theories, the Wilson coefficient is periodic with respect to this rotation fraction, with period being 1. And you can imagine for fermionic theories, the period will be 2 instead of 1. One interesting consequence of this periodicity in the Wilson coefficient for bosonic theory is that, let's say if I have a 3D bosonic CFT, and I turn on, if I set R to be -1 to the power j, then P over Q will just be 1 over 2, right? So in this case, this coefficient would just be 0. So if you compute trace -1 to the power j in a 3D bosonic CFT, then you won't have a linear term in a defect action. We computed the defect action for a 3D free scalar with Z2 flavor twist, and this is indeed what we observed. Okay, I think I run out of time, so I will stop here.
More questions?
Thank you. Is there maybe a simpler version of this where instead of coupling to a non-trivial background metric, you could couple to a non-trivial, say, background field for a global symmetry?
Oh yeah, yes. So, okay. If a d-dimensional CFT has a global symmetry, then what you would need to do is you need to introduce some background fields for a new set of background fields in the d-1 dimensional quantum field theory. And this new set of background fields would come, you can write down new terms you can write down new terms using this new background fields, and then these new terms would have their own Wilson coefficients, but it's not clear to me how this new Wilson coefficients should be related to the original Wilson coefficients in the thermal effective action.
Well, at least for example, you should be able to rederive the 2D CFT version of flavor symmetry. When you vary the partition function of a theory with some Q turned on, then you can at least see how the partition function changes under transformations. You should at least be able to derive that. I don't know what the higher dimensional version of that would be, but is that clear about it? Like in 2D, we know how the partition function changes under like an S transform if you're computing, say, trace e to the minus beta h plus mu q or something for a simple U1, for example.
Okay. Well, no. Let's see. Yeah, I agree, but it's just that if you turn on a flavor twist instead of a twist by space-time symmetry, I think I would need some new parameters to determine the high temperature asymptotics. Are you trying to say that I don't need to introduce new parameters?
Well, I guess all I'm pointing out is that the effective action is still going to be restricted by the same symmetries that, you know, the effective action is restricted, so, you know, you should be able to read off the same coefficients, or at least be able to derive the transformation laws for the partition function. And, you know, perhaps you could use this to put bounds on the way, you know, representations of that global symmetry must appear in the spectrum, for example. It's not obvious. I mean, it's sort of open-ended. I'm not giving you like specific instructions on what to compute. I was just wondering if it's something you guys have thought about.
I think we definitely thought about inserting flavor symmetries, but the conclusion was that we need new background fields and therefore new Wilson coefficients. And of course, I can express the flavor twisted partition function in terms of like this enhanced set of Wilson coefficients, and I can predict its shape. But I have to pay the price of introducing more parameters. That's the conclusion.
Okay.
Yes.
Thank you.
Sorry, in the previous slide, I think you mentioned some general result in terms of the free energy.
Yes.
Is there a simple interpretation of this result in terms of the spectrum of operators of different spins? For example, if I take R to be just some simple rotation or something.
Right. So if you, for example, if you take R to be -1 to the power j, then you will be counting like the differences between even spin operator and odd spin operator, and that's like, okay, I'm just translating the spin refined partition function into a statement about density of states, but I don't see why that it directly tells you the rescaling factor should be q to the power -d.
I'm not making a statement, I'm asking a question. If you can, from this result, extract some statement about the spectrum of, like if the high density spectrum has as many even spins or odd spins or some, I don't know, I'm speculating if you thought about a consequence in those terms or something.
Right. It's definitely possible to translate the rescaling into a statement about spin refined data of your spectrum, but I don't have concrete results to say. Maybe Nathan has something.
Now I have two of them. Another way to rephrase it would just be, you know, let's suppose I take some very large delta and there are operators of all sorts of different spins. And if you take, you know, the number of even spins and the number of odd spins is almost the same because, you know, this difference is sub-exponential. And now what Yixin wrote is a precise prediction of precisely what that difference is. You know, and you have to be subtle with the smearing, et cetera, but indeed, like, indeed, this gives a precise prediction of that. Exactly.
If you apply these ideas to superconformal theories, can you compute the index in this context?
Oh, unfortunately, the thermal effective action doesn't apply. The thermal effective theory doesn't apply to the case with supersymmetry theory because you tend to have gapless modes, which are massless. But like, in order for the thermal effective theory to work, we are assuming that there is a non-zero mass gap. But I think there are ways to probably keep track of how the how this massless modes like affect the thermal effective action, but like that could be less universal.
I have a question about this the first result. So imagine we take R to be some rotation with irrational parameter, then you somehow approximate this rotation by integer q. So is it obvious from this result that choosing different q will roughly give you the same result?
Choosing different q would give
you... Yeah, I'm asking about how to approximate this, how to extract the from this result for the for irrational rotation.
Yeah, you can write down a rational approximation for irrational angles. let's see. And I think you're trying to ask about how does different rational approximations affect the way I approach this.
Right. Yeah.
Let me remind myself of this. Yeah.
Different answers, as you can see, but yeah, so of course different Qs will give different answers, but this is valid when the limit beta goes to 0. So beta needs to be small compared to whatever rational approximation you're making. So if you really were to choose an irrational angle for beta, you need to beta small, but some finite number, and beta kind of acts as a cutoff for what then the best rational approximation is.
Okay. Okay. Also, regarding my previous question, so I think I was thinking about the limit omega goes to plus minus I instead of plus minus 1. Yeah, so I take back my question. Sorry.
Yes, but then, okay, I think this also brings to a very interesting point, which is, you're asking about limit when the omega is plus minus I.
Yeah.
Right, and then you can see from this expression that indeed the thermal effective theory breaks down.
Yeah.
Because you have posed at plus minus I. And, yes,